Adjunct Assistant Professor at the African University of Science and Technology in Abuja, Nigeria. His main research interests are computational studies of microscopic properties of solid-state materials using density state functional theory and its extensions. Dr. Raji is an NRF-rated researcher and a recipient of several research grants and awards. He has used a fair amount of our computational resources, so it'll be very interesting to hear what he's going to tell us about. He looked at two-dimensional materials, semiconductor alloys, biological systems, and high-pressure temperature phases of materials. And over to you, Raji, for to hear your talk.
Thank you very much, Anton, for the introduction. I feel highly honored to make this presentation to these to colleagues elsewhere in South Africa and possibly elsewhere in the world. So the title of my presentation is Density Functional Theory, a Landscape of Recent Applications. So basically, I'm going to give an overview of what we have been doing with the CPU time that has been given to us over the years by the HPC, CHPC. I must say that this is what I'm going to, the presentation is not about everything we have been doing, but an indication of what we have, we have been doing, especially, more importantly, what we have done in recent times. So the outline of my talk is quite straightforward. I will give an overview of the research group, the tools we use and the scientists involved, the personnel involved. And I give since we use density functional theory as our main technique, I will give a basic introduction to it. It's not going to be detailed, it's going to be a short introduction to it. And I'll give an overview of the application. So we have applied DFT so I will give an overview of the application in three main areas: into doped silicene, stray absorption, and the mixed oxides. Now, so an overview of the group. So as I said, we are interested in quite a number of solid-state materials, 2D materials, metal oxide alloys, and transition metal oxide. But we are interested in the bulk and the surfaces. And our collaborators are quite spread all over in South Africa, in Congo, Brazzaville, in the United States. So we have a number of projects, as I've said. Now, so these are not the comprehensive list of material we study, but a kind of a representative list of material we study, and just to give you an idea of what we do on the HPC and the CHPC. So all of us are glued together by the CPU time that have been provided by us by the HPC. So we use the quantum espresso mainly. Some of our colleagues are using Gaussian. So again, we are using exciting to study optical excitation in solids. And we use the AT80 code mainly to study alloy system. So these are the kind of tools we use. And the quantum espresso, the Gaussian, the exciting, the AT80 are all installed on the HPC. And we make use of them from time to time, depending on the interest of our students. Okay, sorry about that. So as I said, I will give a short introduction to the density functional theory. So the starting point is what many of us that are listening to this talk know about. So the starting point is the Schrödinger equation for a single electron moving in the potential. So in our university physics, when we solve Schrödinger equation, we basically look for the electronic. So we are given a potential, then we look for electronic wave function. However, that is for a single electron in a potential. If you have electron gas, so to say, so you have several infinite number of electrons interacting with each other and with nuclei, then you have a many-body problem. So the Schrödinger equation can be recast in the way I've just recast it. So you have basically the kinetic energy operator. Then you have a term that describes the electron-electron interaction. and then you have the term that describe the electron-nuclear interaction. So this is kind of a recast of the basic Schrödinger equation that you and I are aware of. And usually when we solve the Schrödinger equation, what we look out for is the electronic wave function. So basically you are given the potential, then you solve the Schrödinger equation, you have the electronic wave function. And then when you have the electronic wave function, then you can calculate the observables. Now, one of the important observables we calculate is the electronic density, and it's expressed the way I've given it in equation 3. However, if you have, for a real material or a representative material as we study in DFT, the total number of electrons is infinitely large, and it's impractical to solve Schrödinger equation for that. And then the idea of DFT came in some around 1960. And so the basic idea of DFT is that instead of, you have electronic density. So you have the knowledge of electronic density, and then from there, you're able to extract your electronic wave function, and then you have the potential, and then you can calculate all the observables. That's just the basic idea of the DFT. Of course, when we do the recalculations, it proceeds in a different line, but that's just a kind of an outline of how we proceed. Now, so at the heart of the DFT is what we call the Oberg-Kohn theorem, which I will henceforth call HK theorem. So basically, the idea is that it says that relationship between the electronic wave function and the density can be inverted. So it says that if you have a ground state density, it is possible in principle to calculate the ground state wave function. In other words, there's one-to-one correspondence between the ground state electronic wave function and the ground state density. And again, it says that all the ground state observables are function of the ground state density. So it's making instead of electronic wave function, it's making the ground state density as the main object when we do, in a way, in principle, when we solve this Schrödinger equation. So this ground state wave function, it must not only reproduce the ground state density, but it must also minimize the total energy of the system. So it's what I've recast here, that if you have the ground state density, then if you have the ground state electronic density, then you can, that ground state electronic density is given by the ground state wave function. And that ground state wave function is that which minimizes the total energy. That is just the basic idea of the Oberg-Kohn theorem. And if you have an arbitrary density, for instance, so that density, if it is different from the ground state density, so then that arbitrary density that produce that arbitrary with that wave function that produce that density, if it's different from the ground state wave function, then it cannot give this ground state energy. So the ground state energy is the ground state energy is actually minimized by the ground state density. So in a way, we say that the ground state wave function actually is a unique function of the ground state density, and all observables can be calculated as the expectation values of the ground state of the ground state wave function, which is a function of the ground state density. So the most important observables, when we do DFT calculations, what we usually go after is the minimized energy, the optimized energy of the system. And we say that, so once we obtain the ground state wave function, which is a function of the density, then we can use that to calculate the expectation value of the total energy of the system, the Hamiltonian, so to say. And that ground state density, it is the least energy. The ground state density, when it be used to calculate the ground state energy, then that the energy of the system must be less or equal to the energy of any arbitrary density of the system, which we try to minimize. So basically that is exactly what we do in density functional theory. And so in several code implementations you have, whether in the quantum espresso or maybe in VASP or any of these quantum mechanical codes. So this is the basic idea. I don't want to bother you with formulas and expressions which many of us are already aware of and we're probably tired of. So this is just to introduce. It's possible that we have some people here that are maybe students who are interested in this kind of density functional theory, and it's just a basic introduction to it. So if anybody is interested, you can read more about it in some other well-known textbooks. So so over the years we have been using density functional theory to do some calculations, and as implemented in quantum espresso code, for instance, and some other quantum mechanical codes. So as I've said earlier in the earlier part of the presentation, we are interested in many materials, and silicon is just a representation of the two-dimensional system we are interested in. In the past, we have studied graphene, we have studied carbon nitride. Currently, one of the students is working on silicon. So I decided to just give an example of what we are doing there. So silicon is similar to graphene in the sense that they are both two-dimensional system. And it's made of silicon compared to graphene, which is made of carbon. So another major difference between graphene and silicon is, in the case of silicon, it is corrugated. It's not completely planar, at least in theory. It is not completely planar structure. We say it is corrugated, and then we have this vertical separation between the. So there are two types of atoms there. We have atoms. So we have atoms that are designated as 0, and we have another one that is designated as 1. And these two atoms are displaced with respect to each other, so that you have a corrugated system. You have a non-planar system. And the distance between these atoms, the vertical distance is about 0.5, 0.4 to 0.5. In many literature, you see the values are always usually between this range. So compared to graphene, where the vertical, where there's no, graphene is basically flat. And the band structure is like this. So you have this Dirac cone that is the point of intersection at the Fermi level. So the band structure is experimentally, the band structure can be obtained using the angle resolved photoelectron spectroscopy. And so silicon has got no gap and has got 0 magnetization. So in a way, it's similar to graphene. Graphene also, in actual fact, this band structure is almost exactly like that of graphene. So what is our motivation? There have been a lot of advances in instrumentation such that you can manipulate, so you can actually manipulate atoms in materials. For instance, in an experiment done by the group of REN in 2017, they are able to put manganese dimers, pair of manganese in graphene, and they're able to kind of move the manganese around. And we know that even some other experimental techniques are able to determine some parameters of the such single atom that is being manipulated. For instance, in an experiment performed in this particular paper on ion atoms in copper, they're able to kind of put the ion atoms in a particular orientation, and they're able to measure the magnetic moment of the atoms, of the impurity atoms there. So we decided that, okay, so we want to also examine, for instance, how some of these magnetic paramagnetic atoms, how they interact with the silicon structure, and possibly extract some practical applications from such studies. So just to remind you that silicon material is the workhorse of semiconductor industry, and a lot of semiconductor materials or optoelectronics materials are made from silicon. And if you have a two-dimensional silicene, then it is plausible to think of the kind of applications that one can make from it. So there's a kind of enormous potential in studying two-dimensional silicon, so to say. It is two-dimensional silicon, which we call silicene. So we decided to explore the magnetization. Remember, I said earlier that silicene has got zero magnetization. So we decided to kind of explore possible magnetization in silicene and study the spin interaction between the magnetic atoms, and of course, determine the Curie temperature of such any magnetic configuration that we were able to obtain from there. Now, just to remind many of us here, the Curie temperature is the temperature at which some magnetic materials undergo change into the magnetic property. Usually, if you have a material that is ferromagnetic, the Curie temperature is that temperature at which it changed from, say, from that ferromagnetic orientation to maybe antiferromagnetic or even non-magnetic structure. So our model system is just vanadium. It's paramagnetic vanadium metal atom, which we want to use that to study magnetization and spin interaction in silicene. So we know from previous study that vanadium has got magnetic moment in silicene. And then we want to study just a small cluster of this metal in silicene. And we want to start small. So we have chosen just vanadium pair, and then we put that in silicene, and then we study the induced magnetization and interaction between the spin center that are introduced by the vanadium atoms. So our model system is this. So you have, so let me just remind you that, so in this kind of, in silicene, there are two possible defect position. You have the substitutional position, which is just replacing any of the silicon atom with any purity atoms you want that you have, and then you have this defect center that could be the center of the hexagon. Now, so what we want to do, so basically what we want to do is to try to use this. So we try to use this vanadium and put them inside these defect centers in silicene. So our model system will consist of having a pair of vanadium atoms that are separated by silicene atom. So for instance, if you have so in the case of substitutional position, you can have vanadium atom at 1. So you have vanadium atom 1, you have another one at 2, or you have one at 1 and you have another one at 3, one at 1 at 4, or you have 1, 5, 1, 6, and so on. So basically you have two vanadium pair that are separated by silicon atoms in silicene. We also consider this configuration where you have the vanadium atoms that are in all position, center of the hexagons, and then you have like, they are separated along like A, B, A and C, and so on. But what you have to take note of is that, you remember I said initially that silicon atom has got there are two types of silicon atom in silicene. There's one that is, and two of them are displaced with respect to each other. So when you put an atom at 1, for instance, so atom 1 and 2 are in terms of the local environment, they are different. Now, if you put atom at 1 and atom at 2, you are putting these two vanadium atoms at two different lattice positions. If you put 1 and you put atom at 1, another one at 3, so you are putting vanadium atom at 2 at the same lattice position. So So what we are doing here, we are exploring two things here. The separation between the atoms and the influence of the so we're investigating two things here. One, the distance of the separation of the vanadium atoms, and what the lattice location will do to the magnetization that we are trying to study. So then we have two vanadium atoms, for instance, that are at this lattice position, and they have different magnetic orientation. So we have antiferromagnetic orientation, then we have the ferromagnetic orientation. In the case of antiferromagnetic orientation, the vanadium atoms are oriented in opposite direction. In the case of ferromagnetic, they're in the same direction. And so when we put two vanadium atoms in the lattice, we consider these two orientations, right? So, and of course, then we separate. So we separate them. So we measure we study the structures in terms of the magnetic orientation and the separation between them. The same thing we have done with the whole site. So again, we have the antiferromagnetic orientation, and we have the ferromagnetic orientation. Now, so let me just, so we have so before I go to the detailed result of this vanadium dimers, just to remind you that if you put a single vanadium in silicon, it induces magnetization in the structure. So you have vanadium atom, we acquire a magnetic moment of about 3 Bohr magneton, and if it is at the interstellar position, it is about 4 magneton. And we also find out that it is much easier so when we calculate the defect formation energy, we discover that vanadium has got formation energy that is like negative, and substitution position is about 2.47. But the meaning of this is that based on the way we've written the formation energy, the more negative the formation energy, the easier it is for such a defect to form. So based on that, it's easier to actually put vanadium at the interstellar site, at the center of the hexagon, compared to the substitution site. And then, if you look at the band structure of that structure that contain vanadium, you discover that the Dirac point is completely destroyed. But then you have this splitting of the spin. You have up and down spin that have now been disentangled in such a way that they are now separated. And normally when we do band structure calculation, we have this separation of the spin, a separation of the bands is an indication that the material is actually magnetic. In the case of interstellar old position, the Dirac position is preserved. And yeah. So back to the vanadium pair that we talked about. So what we discover is that so we have named this in such a way that, so if you look at the first column, so when in the substitution position, when the silicon atom are just at the nearest position, when there's no silicon, when the vanadium atom are at the nearest position to each other, and there's no silicon atom that separate them, then you have this zero silicon. When they're separated by 1 silicon, then we have this. When they're separated by 2 silicon atoms, then you have that, and so on and so forth. So again, if the atoms are not separated by, if the vanadium atom are not separated by any silicon atom, then the atoms are at different sublattice positions, as I've shown you earlier. If they're separated by 1 silicon atom, then they are in the same lattice position, and so on. And these are the distance of separation, because as we increase the separation of as we separate the atoms, then the distance also increases. And then the most important thing here is this column, the yellow box. So what you will notice here is that as we increase the distance between the vanadium atom, we discover that there's a kind of flipping in the stability of the relative stability of the magnetic orientation. For instance, when the atoms are separated by just one silicon atom, then we discover that the antiferromagnetic orientation of these vanadium atoms are the most stable. They have the least energy, lower energy, so to say. When they're separated by two, the ferromagnetic orientation becomes the most stable. Again, when they're separated by three, and so on and so forth. So as we separate the vanadium atom in silicene, so we have this flipping of the stability of the relative stability of the two kind of magnetic orientation we have studied. For now, let's leave this third column. I will come back to it later. Now, so again, I've just repeated what I've just kind of summarized what I've just said here. So what we see here is that actually the relative energy of the antiferromagnetic and ferromagnetic orientations are quite small. They are order of milli-electron volt. But when they're separated by just one silicon atom, we have this high relative energy, which actually show that the antiferromagnetic orientation is actually more stable. But what is very clear here is that there's a pattern of site dependence of the ground state energy, and it's very apparent from the oscillation of the relative stability of the antiferromagnetic oriented configurations. So, yeah. Okay. And for the whole configuration, we didn't see that. The only thing we can see there is that when the two atoms are at the nearest positions, that center of the two hexagons that are very close to each other, the ferromagnetic configuration is quite is more stable than the ferromagnetic by about 0.1 E4, 0.14 EV. Okay, I've just repeated it. So this is just to summarize what I've just said there. Now, so now what we should take note from here, especially in the case of the old configuration, is that there's a small energy difference between the antiferromagnetic and the ferromagnetic configurations. Now, for those who study spintronics and who make use of magnetization for practical applications, the implication is that you can actually switch between these. For instance, if you look at, oh my word, sorry. Okay. So if you look at this this particular defect configuration, for instance, so you can see that the energy difference between these are quite except for this particular one, when the vanadium atoms are separated by one silicon atom. Otherwise, the other energies are quite small, and it means that you can flip easily between this antiferromagnetic and ferromagnetic orientation. The same pattern is observed here, except for this one, which is about 0.1 E4. Otherwise, you can flip easily between. Okay, sorry, this one is supposed to be three holes. Now, from a practical point of view, so if you can, so this switching between the antiferromagnetic and ferromagnetic orientation, that can be achieved by external perturbation such as electric field, and you can use pressure or even photonic excitation. And so even for things like quantum information storage on things like that, this can be considered for such application. Again, so we determine the formation energy of those defects, and the most important thing here is that the formation energy are all negative, and which basically means that when you put vanadium in silicene, so there's possibility for you to have a stable material there. So so when you separate, so again, when the atoms are quite, if you look at the yellow, this yellow thing, that yellow circle that I put here. So you see that when the atoms are quite close to each other, they're separated by just where they are. Vanadium atoms are at the nearest position to each other. Information energy is the most negative, and that particular, and when they are separated by just one atom, their information energy are quite at the most negative, and they're the most stable configuration. For the whole configuration, the same thing here when they are quite close to each other. And these are the, so this pink, this gray sphere are the silicon atoms. So that's the most important thing that I want to bring out here, that the information energy are all negative, and that means that you can actually, in practical terms, you can have this vanadium in silicon. Now, so again, we look at the unit density of state. What we can see here is that, remember that we said that silicon atoms are, so silicon is non-magnetic, and so, and basically the way we see that is that, so it's non-magnetic. We can see that from the density of state. But what you observe is that if you put two vanadium atoms here, I've represented them by the red balls. And if you look at the silicon atom in between them, and we calculated the density of state, we discover that, if please just pay attention on this shaded region. Now, for the solid line is for the silicon atom, and what we see clearly from here is that the intervening, if I just use that word, if I may use that word, the intermediate atoms between the vanadium, the intermediate silicon atom between the vanadium atoms, they now have a different density of state, and they have, so the density of state have got instead of 0, they've got a finite value, which is indicative of the fact that these intervening atoms have now acquired some metallicity. They basically become metallic, which is quite interesting to us, because if you look at, when we did the density of state calculation for all the other atoms here, they basically have the shape for the pure silicon atom. They are basically non-magnetic. So we did that. So we did the density of state calculation for all the atoms that are in between, and we discovered that they have acquired some kind of metallicity. So again, we did that for several of the structures, and we observed the same thing. So even for the whole structure, we observed the same thing. The intermediate atoms between the vanadium atoms have acquired this kind of, they have a finite density of state, which means they have become metallic. So what I will, okay, so so again, we try to look at deeper into the magnetization, and what I'm trying to say here is that as soon as you put vanadium in silicon, then the supercell will acquire some magnetization, and these are the kind of values that we have here between, you have when the atoms are quite, so you have to pay attention to this. When the atoms are quite near, very close to each other, the magnetization of the cell is 0, but when they are far from each other, they have a finite value. So what I've shown here is for the stable configurations. And what I'm trying to show here is that here in the lower panel, now, so what I'm trying to show here is that when you have these vanadium atoms in silicon, when they are separated, so when they are near to each other, they have 0 magnetization, but when they are separated, they have a finite magnetic moment. And in most cases, the magnetic moment are quite close to that with free vanadium atom. So what this tells us is that if you put vanadium in silicon, in as much as they are not close to each other, you can still have, you can still preserve the magnetization of the vanadium atom. And therefore, in practical application, vanadium practical application that would require some that require magnetization of this vanadium atom of the silicene, then you can have a situation where so you can have a situation where you're able to preserve the magnetic moment of the vanadium atom. So in a way, silicene can serve as a substrate of vanadium atoms, and it preserve the magnetization of the vanadium atom. That's just the main message here. And again, then we try to look at, remember I said earlier, when I showed the density of state plot, that those intervening atoms they acquire some magnetization. So we are just using the density, three-dimensional magnetization plot to demonstrate that here. So, but the most important thing here is that if you look at, so the big blue and the big red balls are the vanadium atoms that are separated by some silicon atoms. Now, what you see from here is that, so this particular one, for instance, this vanadium atom, this blue 3D magnetization density plot, this particular one is representing a particular magnetic orientation, say spin up, for instance. Now, the atom next to it acquires a spin rotation that is directly opposite that. And then as soon as you go from there, if you go from there, if you trace the intervening atoms up to the other atoms at the second atom, you see that you have this kind of spin up and spin down orientation of the silicon atom in between them. So we did that for configuration that have just 5 atoms here. When you have the vanadium atoms, in this case, the atoms are antiferromagnetic, they have different orientation. Here they have the same orientation, but we see the same thing in the sense that the vanadium atom induces magnetization of a different spin, of opposite spin actually, next to it, and that propagates in a way as you propagate in between them. So there's a kind of, and this kind of, so when you have this magnetization of the atoms in between, then that means the spin center, the vanadium spin center, are able to interact in a way. And so this kind of interaction is called the super exchange interaction, and is facilitated by these silicon atoms, which has got the p orbitals. And so in a way, again, the vanadium atoms, because these are now magnetic, so they provide some conducting electrons to the system. So here we try to, so when we have these 2 atoms in the system, they're stable, they are coupled together in a way. So the way we determine the strength of the coupling is when we calculate what we call the spring exchange constant, which determines the strength of the coupling between the vanadium centers. So okay, so we use the Heisenberg formalism to determine the spin exchange constant, and so then we selected. So we selected the 2 ferromagnetic configuration of the silicon atom, where the 2 ferromagnetic configuration of the vanadium atom, where the atoms are separated by 2 silicon atoms. So we obtained the spin exchange constant between 3.3 eV, and we calculate the Curie temperature using this formula. So when we check the literature, what we discover is that there are quite a number of formulas that they use to calculate the spin constants, spin exchange constant rather. Many of them are derived using using quantum mechanical technique, or are derived using some other formalism. But in any case, we try to find the Curie temperature, and so we discovered that for the ferromagnetic coupling of the vanadium atom, when the atoms are nearest to each other, separated by almost zero, so basically the atoms are coupled together, they are separated, they are the center of hexagon, and they are next to each other. So we obtain the cooling temperature be 394 Kelvin, which is greater than the room temperature. So again, when the ferromagnetic for the so when we use another formula for that, which we also obtained in the literature, we got something like 520 Kelvin. So the most important thing here is that we're having a cooling temperature that is now greater than the room temperature, which is quite a theoretical achievement, so to say, in the sense that what people, for practical applications, you want a magnetic orientation that is stable, even at room temperatures. So in a way, that's exactly why this kind of cooling temperature is quite important from practical point of view. So that is about silicate. So another thing we have done is to use to apply the X-ray absorption edge spectroscopy, and we applied that to study ion at extreme temperature and pressure. Now, so again, quick recap of X-ray absorption spectroscopy. Basically, you use a photon to excite electron from the bond state out to the continuum above the Fermi energy, and then you acquire the absorption spectra there when you do that. One good thing about the extra absorption is that it's element specific. You can focus your photon beam on a particular atom, and then you obtain the absorption spectra. So normally when you add KH, it's basically means that you have excited electron from the S state, from the bond S state to the continuum above the Fermi level. When you excite electron from the 2s level, then you have the what we call the LH, and so on and so forth. So again, it is just kind of another view of the same process. So basically, you shine photon light of appropriate binding energy onto electron, then you excite onto the continuum, and then in the process you acquire the S3, you acquire the absorption spectrum. Now, how is that? So, okay, so this is how we calculate theoretically, this is how we calculate the absorption spectrum. So it's basically this formula, and so you excite, so you have a, so you have this transition amplitude that couple the final state and this distributive initial and the final state. And so the typical extra absorption spectrum looks like this. So there are some terms that we use. We say we have the shape is usually like this, and then you have the pre-edge, and then you have the edge, and you have the continuum. Most of the absorption spectra are in this shape. And so extra absorption, people use it for different applications. For us, we're interested in how you can get some structural information from using the X-ray absorption. So that's our interest here. People in chemistry or catalysis, they have different applications to determine certain things like the ligand field and spin state and all that. For us, we are more interested in the structural information of the material we are studying using the X-ray absorption. Now, so our interest is in the ion at extreme pressure, as I've said. Why is ion important? Ion is an important component of the Earth core. And so the knowledge, people in geophysics are concerned about it because it's one of the important components of the Earth's interior. And when it melts, ion in a liquid state, it has some implication on the Earth's geomagnetic field. So, and it's also very important in determining the thermal profile of the Earth interior. So the idea is, so the most important thing is that it's one of the most important elements in the Earth interior. So, sorry. Okay. So what geophysicists are usually concerned about is, okay, so people have performed experiments where they produce the phase curve of ion. And what some of the plot phase diagram have said is that at about 80 GPa and at about temperature of about 2,700 to 2,800 or thereabout, ion is a liquid material. Now, so this is the kind of thing so if you put together an aggregate of several phase diagram of ion, so what they say is that at about 70 to 80 GPa and temperature of about 2,800, then you have a liquid ion, so to say. And then, so some few years back, we discovered that there's an experiment that was done by Prof. Boiler in Germany. And basically, what he did was that he used this X-ray absorption technique to sort of fingerprint a liquid ion. So he acquired the X-ray absorption structure cross-section for ion at room temperature, which is the first one here. And then he acquired, of course, at temperature of 78 gigapascal. Then he acquired the same, for the same ion, at the same pressure of 78 GPa. He heated the ion to 2,300 Kelvin and acquire again the X-ray absorption and at 2,900. And what he claimed was that at 2,900 Kelvin and the pressure of 78 GPa, he said that certain features of the X-ray absorption are indicative of the melting. Now, if you compare what is claiming here with this particular phase diagram, see there's a consistency, because at about 80 GPa here and about anything above 2,500, anything above 2,600 here, ion is liquid. So that's exactly what he's trying to say here, and he's basically trying to use this extra absorption as a fingerprint of liquid ion. And so he said that one of the things is that what happened is that this pre-edge structure basically disappear when ion melted, and this peak shift a little bit, and it basically flattened to some extent. And this soldier here they also disappear at melting when ion has melted. So in essence, the X-ray absorption spectra square is kind of giving some credence to the phase diagram of ion that has been obtained before. Now, so when we saw this paper, we said, okay, so we spoke to, we have a friend who has developed some classical potential for ion. He has used basically modify embedded atom potential method to develop classical potential for ion. So, and I don't want to go through the detail of the potential development, but if anybody who's interested in that can check this paper. But what he has done is he has used this idea of this force matching method where they match arbitral forces and stresses to obtain some of the parameters of this potential. So in any case, we took the potential, we implement that in the classical potential, in the classical molecular dynamics code. Sorry. So one thing about that classical potential that Liao is the name of the guy. Yes, one of the important things has done is that the parameters of the classical potential are fitted to 80 GPa and at this temperature. Now that potential is transferable within this window of 30 GPa and 500 Kelvin, and he showed in that paper that this potential actually reproduces the lattice constant, diversion coefficient, and viscosity that are consistent with the experiment. So, the parameter of these potentials are such that they're able to produce the the elastic constant and the diversion coefficient and everything, classical properties of ion at this particular pressure and temperature. So we took the potential and then we implement that in our classical molecular dynamics code. We perform a molecular dynamic simulation to generate structures that corresponds to ion at 70 GPa and at this temperature of 300 Kelvin, 2300 and 2900 Kelvin. We used 250 atoms for the simulations. And then, so we acquire so we produce the S3 absorption. So what you see here, so the solid curves are the experimental curve, while the liquid, while the dotted one are the one we produce through our simulations. Now, what is important here is that just as experiment claim, at 78 GPa and at 2900, we observe exactly what experiments have discovered, that this pre-edge structure disappeared, and this peak that I have named D and E here basically flattened. And so we agree with the early experiment that says that that says that ion is actually liquid at this pressure, 70 GPa, and at 2900 Kelvin. Of course, there are some other things we have done to confirm that ion is actually liquid. It's liquid at that pressure and temperature. But the most important thing is that we're able to confirm that indeed the disappearance of the pre-edge peak and the flattening of this peak at higher energy are actually an indication of the melting of the ion. So, but again, you see that our theoretical calculations are not exactly the same as the theory as experiment. For instance, at room temperature and at 70 GPa, we are not able to produce this B and C curve here, and that is the same thing here. But finally, what we know is that at the final curve, what our final curve basically totally agree with what experiment has produced. That is the disappearance of the pre-edge curve, the flattening, and almost disappearance of the curve at D and E, and the disappearance of the other peak at B and C. And so we say that there could be many reasons for that. So there are, if you have included the influence of phonon, probably will have a better result. Of course, the experimental sample is different from ours. The experimental samples has got some other defect, which we have not able to reproduce in the experiment. So we expect some discrepancies there, but nevertheless, we have some appreciable similarity between the experiment and the theory. And we make that we presented that paper in high pressure conference in London in 2010, no, 2015 or thereabout, and it was widely appreciated and considered as one of the important contributions to high pressure physics. Okay, so we continue to apply this S3 absorption to iron oxide, up to oxide material, and so we applied that to cobalt. Cobalt oxide. Cobalt oxide is an important material for those who study catalysis, water separation, and things like that. So just an introduction to the structure. It's a normal spinel structure. It's got two sides for cobalt. There's this cobalt ion that is surrounded by octahedral ion, and there's one that's surrounded by tetrahedral oxygen and octahedral oxygen atoms. So you have these two types of cobalt atoms in a spinel. So from previous experiments, the they've used extra absorption to show that there's a reduction in the charge state of the cobalt for when they do alcohol oxidation on the cobalt oxide surfaces. So again, this particular cobalt oxide have been used for water dissociation, to study dissociation of water on a cobalt oxide 001 surface. And again, they use X-ray absorption to identify the active site for the water oxide water dissociation. So X-ray absorption has been is quite useful for this kind of study. So one of our colleagues is studying this cobalt oxide for catalysis, and he said he wanted a theoretical insights into this X-ray absorption because there are some things that he would like to do in the future that experimentally could be quite expensive. So he basically wanted us to help him to calculate the X-ray absorption spectra for the oxygen atom and the cobalt atom. So we set out to do that. So our starting point in that case, also let me just emphasize that the work is ongoing. So the whole idea is to acquire the X-ray absorption, to calculate the X-ray absorption for oxygen. And so when eventually that cobalt atom is used for catalysis applications and whatever application they're trying to do there, we can use that some features on the X-ray absorption to kind of monitor some catalytic reactions when the cobalt oxide is being used in typical laboratory setup. So they synthesized the cobalt crystal, and so they did X-ray diffraction, and they said that X-ray diffraction shows exactly that they have synthesized the correct cobalt oxide and all that. They gave us this lattice parameter to be about 8.1, and they said, okay, with this lattice parameter, can you calculate the oxygen KH for oxygen KH in cobalt oxide? In the meantime, they have also obtained experimentally. They've obtained the oxygen KH, in their using one of these control facilities in Europe. So we acquired the oxygen KH, and we have a very good agreement between the one they have calculated, the one we have calculated. There's a good agreement between the one we have calculated and the experimental oxygen KH they have acquired, and we're excited about this. So the next thing is that what they will do next is that they're gonna use that oxygen, this cobalt oxide nanocrystal for catalysis to study some chemical reactions, and we shall be using in the nearest future. We shall be using some of the features of oxygen KH to monitor the catalytic reaction. Basically, that's the main idea. So this is just to confirm what the theory says. We calculate density of state for the oxygen, and when we obtain the density of state for the oxygen atom for the unoccupied density of state, and we compare that with the oxygen KH, there's a similarity between them, which basically means that so the oxygen absorption we have calculated is actually due to the excitation from the S state to the 2p state of oxygen. So this is just a proof of concept, basically. So as I said, the whole idea is that when the cobalt oxide is exposed to real life reaction condition, the oxygen spectra will change, and then we see how that actually, what that says about the kind of reaction they are using the cobalt oxide to study.
Hi, Raji, we're running out of time. If you can
Okay.
get to summarize quickly,
Yeah.
maybe we can get some questions still.
Yeah.
Anyone
Yes.
has questions for Monte?
Yeah. So thank you. Just about five, just about two. So the other one, other we have studied is the oxide alloys. This is quite very simple. So what they are trying to do here is to mix nickel oxide and zinc oxide, and they want to obtain novel property. Let me just say here that when you mix oxide together, you are trying to modify the electronic structures and electronic properties of the material. So what we did with DFT is actually to assist to give an indication of the okay. So so what we did with DFT is just to give an indication of that concentration at which there's a phase transition between the woodside phase and the oxide phase of zinc oxide when we kind of vary the stoichiometry of the nickel dopant. So again, the good thing is that we have the concentration of the dopant at which there's a phase transition and it's in agreement with the experiment. Again, this kind of studies is ongoing. Again, we are continuing our study to characterize that material using many body perturbation theory, and we want to study the effect of dopant and its effect on the alloys. Thank you very much.
Thank you, Raji. Does anyone have any questions? I'm not seeing any on the chat at the moment. I have a question for the interim. Raji, I'm wondering with the CHPC part of the work, we're using quantum espresso. How are you finding the scaling? How many nodes are you using? I don't think the calculations are that memory intensive, but they may be quite CPU intensive. If you could elaborate a bit on that, and let's see if anyone can add more questions too. I have a specific question as well.
Okay. In terms of memory, I think we are still okay. The memory requirement is order of gigabytes. So, but very, very soon we should be doing this GW calculations and many body calculation. So these are usually computational intensive in terms of memory and the length of time that the calculation will take. So we see exactly how that goes. But for now, we're still okay with what we do.
Okay.
With what's this? Yeah.
Okay, so that the big mem nodes might be helpful, but we'll have to look when we get there.
Okay. Yeah.
Okay. Here's I see a question from, I see Krishna. Let's see if any other questions. Krishna asked, how are you dealing with the temporary files written out during Quantum Espresso run? Are you managing to remove them as well?
You mean the scratch files?
The Quantum Espresso creates a lot of temporary files after the runs, yeah.
Oh, yes. So, okay. So usually so most of these temporary files, so if the calculation is continue, we don't remove the temporary files, especially when we want to restart, if you have to restart the calculations. But sometimes when we run to storage problem, what we do is that we don't restart the calculation in the classical way. What we do is that we remove all those scratch files, then we use the last atomic coordinates of the structure we have reproduced to restart the calculation. So that has been quite helpful. But in most cases, the way quantum espresso has been written these days, in terms of, I don't know exactly what's going on there, but it doesn't really, we are not having much problem with the storage. The big thing is maybe it's something that the CHPC may have to look into is this post-processing. Because when we want to do the post-processing, we have to take all these files from the HPC to our local desktop. From there, we do the post-processing, and sometimes this can be order of several thousands of gigabytes, sometimes close to a terabyte. And so if you don't have a quite big storage on your desktop, local laptop, then you have a big problem there. So it will be, maybe to be helpful in the future if you're able to do some of this post-processing on this HPC, so that we don't have to import these files onto our local desktop. I think that's something that that should be looking into in the future.
I think we must discuss that. So what are you using for post-processing, Krishna asks, and we should be able to do it directly on the cluster, as I think if it's not a GUI.
So this, like the charge density plot I showed, so we use this SCRISDEN for that, the visualization software, and the input to the SCRISDEN comes from the one of the modules of the quantum espresso, right? So so what you guys can do is actually if you're able to find a way on how we can use SCRISDEN on the CHPC, I think that's the main thing, to use SCRISDEN on the CHPC so that we can visualize it, so that we can plot some of those post-processing, and then find a way to now import our nice pictures onto our local desktop. That would be a big leap.
It's worth looking into. It's not as easy if there is a GUI, which SCRISDEN is essentially. So it's a visualizer. So, but we can discuss it. I know Charles deals a lot with that type of thing, so he might be a person to be chatting with a lot more on that. So we can discuss some of the details. It might be, and as I say, with the temporary files in Quantum Expresso and other codes, it's good for any other users if they're not needing any temporary files of any sort to remove them as well when you can.
Sorry, Anton, is there a delay? Or is it just me not hearing? Anton, are you there?
I think Anton having an issue.
I can hear you.
Okay, Dr. Raji, I think Anton is having an issue. I think we are running over time, but I just want to ask a very quick question.
Yes, please.
Of course, your research program at CHPC, we regard as one of the bigger ones. I mean, when you go into, say, millions of hours in a 6-month allocation period, it is quite significant. But I noticed that your collaborations in terms of the members of your program is I think almost all of them are based outside of South Africa. It's I think Congo Brazzaville is quite prominent.
Yes.
Can you maybe just give us a bit of background? How is your collaboration set up? Are all your collaborations externally, or do you have also, say, collaborations within South Africa, or maybe students that can participate in this program?
Yes.
Thanks.
So this is kind of I've mentioned this to. Okay. So I've mentioned this to Anton at the point in time. The initial problem is having. Okay. So first of all, it's the nature of my job here at UNISA, which is not a long-term contract. And when you're not on long-term contract, you have to be very careful with how you admit students. Because if you say, for example, if you have a 2-year contract, to admit a PhD student could be a challenge, because after 2 years, your contract may not be renewed. So if you have a 5-year contract, then you can think of, admitting PhD student and all that. So what is happening is that with the so at the moment there is a PhD student that is working with me and Prof. Lombardi. So the other guys that you are referring to, the Congolese guys, are my long-term collaborators that I met where I was also a PhD student. And so some of those guys have grown to become professors in their respective institutions. And so they will continue our collaboration in that sense. So for me, there's no restriction to having local collaborators, so to say. There's no objection to that. The only bottleneck is just that I'm on contract at UNISA, and there is a limitation to which you can admit students, supervised students on a long-term basis. If in the future, if that restriction is not, if that bottleneck is not there, then I'm sure there will be more local content in terms of the number of students that are co-supervised.
This is perfectly in order. I was just of interest that I don't know. Of course, PIs based in South Africa can collaborate with whoever they need to. So this is perfectly fine. I'm not sure whether Anton is back, but we are running now quite a bit over time, Dr. Raji.
Yes,
so are you back, Anton? Okay, so you can
sorry.
conclude from your side. Yeah.
Sorry, I lost my link. Sorry, I had one other quick question on the actual science with the silicines. Would it be of any use to be looking at one vanadium substitutional and one interstitial, those sort of situations, which you looked at only one or the other? I don't know if that works or is of interest, or maybe a very quick reply.
But I don't really understand the question. But normally, what we do is, so what we do in that kind of situation is that, because there have been previous studies that have done single atoms, and we're interested in cluster. So when we do the single vanadium atom in silicene, we compare with what have been done by others and what have been done in the experiment. And once we have a good agreement, then we can say that we have our calculation parameters are well set to study more complicated structures like clusters and 2-dimensional, 3-dimensional clusters on silicene. So it's just when we study a single vanadium, it's just to kind of benchmark our calculation parameters to see that it actually produce what has been produced in some other papers, and to see that we have some results that are consistent with what has been done in the experiment. Because when we study dimer in silicene, that we don't have experimental data for that, but we have experimental data for single vanadium in silicene. And so once we reproduce those things like magnetization, things like the density of state and band structures that has been obtained in the experiment, then we can have much confidence to go ahead and do more complicated defect structures, vanadium structures on silicene.
Okay, now I was actually wondering, like, one substitution and one interstitial together, and whether that. Okay.
Oh, okay. Okay, that would be quite useful. Something I think we did that. Yeah, but I've noted that. Thank you very much.
Okay. Thank you so much for. Good to be hearing from you again and to learn what you've been doing. I'm not aware of any other questions, and thank you so much for your presentation. And hopefully we can see you at one of the CHPC conferences as well soon.
All right. Thank you very much.
Thank you everyone for attending, and sorry that we ran a bit late.
Thank you.
Okay.
Thank
Thanks,
you. Thank you
everyone.
very much, Dr. Raji.
Okay, bye.
Appreciate
Thank
it.
you very much. Thank you.